inequalities. Yeah, this is some of the content I did go through last session, but I think we can brush up on a bit of it. So today we will cover AMGM and the power means inequality, and then we will talk about the rearrangement inequality as well. So I think last time we would have left off by doing question 4 in the AMGM snacks. So I think what we can do is we'll talk about rearrangement inequality a bit, and then we will go back to AMGM and then go over some problems. Okay, so the rearrangement inequality. So this is an inequality based on finding like the maximum or the minimum expression of like a permutation of two sequences and then how they are multiplied. So I guess they're dot product. So here we have our numbers a1, a2 all the way to an, and then x1, x2 all the way to xn. Then we can understand that the expression E is maximized when the two sequences are sorted in the same way. That is, the largest number from one sequence is multiplied by the largest number of another sequence. The second largest is multiplied by the second largest of the other sequence, and all the way down until the smallest one is multiplied by the smallest number of the other sequence. So that is how you would get like the maximum. On the other hand, if you wanted to find the minimum, the minimal expression, then you would sort the sequences the opposite way. So from one sequence of numbers, you would multiply the largest one, and then you would multiply that with the smallest number from the other sequence, and then you would kind of reverse that order. Is that clear? Let me know if anyone has any questions. If not, let's just do a simple example. Okay, hold on. I'll just open up a page in my notes so that we can give it a go. Okay, so let's suppose I'll start sharing again. Let's suppose we have one sequence of numbers. It's going to be like 3, 4, and 5. And then we have another sequence of numbers like 1, 2, and 6. Now, what would the maximum like sum of the products be if you were to take these two sequences? How would you pair up the numbers from this sequence and this sequence so that when you multiply them and then add them up, you get the maximal sum? If you have any ideas, let me know. Okay, so if we were to pair them up like this, so 3 multiplied by 1, 4 multiplied by 2, and then 5 multiplied by 6, then we would get our maximum. So what would that be? That would give us 3 plus 8 plus 30, which is going to be 41. Ooh, okay. Now what happens if we want to find like the minimal one? Then we would order it the other way around. So instead, we would want to change 1, 2, and 6 so that it's like ordered in the opposite way from largest to smallest. Then we would have 6, 2, and 1. And then we would pair it up like this. That would give us 18 plus 8 plus 5. And that's going to be 31. So for our maximum, we found 41. And for our minimum, we found 31. Okay, so this is an example of how the rearrangement inequality can be used to quickly see which way is gonna like produce the highest sum. Okay, cool. So let's try some of the problems. Okay, so firstly, we're going to try this one. For positive real numbers a, b, and c, prove that a cubed plus b cubed plus c cubed is greater than or equal to a squared b plus b squared c plus c squared a. So I'll give you like 5 minutes to give that a try, and let me know if you have any questions. Okay, does anyone have any ideas? If not, then I can go through the problem. Okay, so let me just take a look at the problem statement again. Okay, right, so we want a cubed plus b cubed plus c cubed greater than or equal to a squared b plus b squared c plus c squared a. Okay, let's try that. Okay, so I'm gonna put RTP because we're required to prove this. Okay, so we can try to think about how we can construct two sequences and then order them, right? So what we can do is we're going to suppose that A is the largest one, right? So suppose that A is like greater than or equal to B and C. Okay, so we can't say for sure, we can't, without loss of generality, assume that B is greater than C just like this. Because on the right-hand side, our expression is not symmetrical, right? If it was symmetrical, then we would also need like a b squared a and like a c squared b and like an a squared c, right? But we're missing those terms. But what we can do is consider two cases. One, if b is greater than or equal to c, and then also one where c is greater than or equal to b. Those are both cases that we need to consider. Okay, so let's just call this 1. Let's just call this 2. So in case 1, then we have A is greater than B, which is greater than C. What does that also mean? Well, that means that A squared is going to be greater than or equal to B squared, which is going to be greater than or equal to C squared, right? So from this, what we can do is we see that we now have our two sequences, A, B, C. And because we have ordered them in the same way, from largest to smallest, then when we take the dot product, so we multiply a by a squared, b by b squared, and c by c squared, and then we add them up, then what we get from that is going to be our a cubed plus b cubed plus c cubed, right? So this is what we have. And because of the rearrangement inequality, we know that this is the maximal possible permutation. So we know that anything that is not this, essentially, will be smaller than it. So let's just check how this is going to be true. So we know now, instead, for our other sequence, we would have A, B, C, but we're ordering it with, what is it? It's going to be C squared, and then A squared, and then B squared, right? So we've kind of mixed up the order so that the smallest one in the second sequence is getting multiplied by the largest one in the first sequence. So therefore we know that this is not maximal. And consequently, you have finished the proof for the first case. Now, remember we have to consider two cases because we cannot, without loss of generality, assume that one is always going to be bigger than the other. So now we have to consider what if C is greater than or equal to B. So then we would have A greater than or equal to C greater than or equal to B. And consequently A squared greater than or equal to C squared and greater than or equal to B squared, right? So we have the same logic as before. So now if we were to order it like this, A squared, C squared, B squared, and we took the dot product, then we would get A cubed plus B cubed plus C cubed, which is maximal, right? That's what we got on the left-hand side. We know that anything smaller than it will not be maximal, and the inequality should hold. But let's just see what we get. if we order it differently. So then we would need A, C, B. So that's an order from greatest to least. And then what would we multiply that by? Then the A term would be multiplied by C squared. And then the C would be by B squared. And then B would be multiplied by A squared. Right. And then now we can see that this is in order from greatest to smallest. But this one, you're starting with the smallest one, right? C squared. Then you're going to be taking the one in the middle, B squared. And then you're going to be, wait, no. C squared is not the smallest here. My bad. You'll be multiplying the greatest one by the middle one, C squared. Then you'll be multiplying the middle one by the smallest one, B squared. And then you'll be multiplying B, the smallest one, by the largest one, A squared. So clearly these are not ordered the same way, right? So because of that, you know that it is not going to be maximal and the inequality will hold. Okay. Um, Let me know if you have any questions. Okay, if not, then we will move on to the next problem, which is also like a similar kind of logic. You just have to complete one other step beforehand. So yeah, kind of similar thing. Just have to be trying to do one more step to make it work. Okay. All right. Okay, so question 2. Can you give that a try? I'll give you guys like 5-10 minutes. Hi guys, let me know if you've made any progress. But I do have a hint, which is that, you know, if A is greater than or equal to B, then log of A is also going to be greater than or equal to log B. Because log is like an increasing function. So it's like that's something like that. So this property holds true. So that is something that you can use if you can think of how to use it. We'll keep on working on this for 3 more minutes, but if you have any questions, feel free to just unmute and ask, because I also can't like see the chat when I'm sharing screen. Okay, let's give this one a go. So what do we want to prove? We want to prove that a to the power of a times b to the power of b times c to the power of c is greater than or equal to, I think it's a to the power of b, then b to the power of c, and then c to the power of a. Okay, so firstly, let's think about how we can order this, right? So we can assume one of them to be the greatest without loss of generality. So let's suppose that a is greater than or equal to b and c. Out of b and c, are we able to assume that without loss of generality, one of them is the greatest? The answer is no, because once again, this is not symmetrical, right? You do not have b to the power of a, you do not have c to the power of b, and you do not have a to the power of c. So therefore, we have to try both cases. So we have to consider what happens if b is greater than or equal to c, and what happens if c is greater than or equal to b. So let's call these our two cases again. Okay, so let's think about how we can use our log laws to kind of break these two things down. So because of our log laws, what happens if we take both sides? Well, proving this expression is like the same as proving that log a to the power of a times b to the power of b times c to the power of c is greater than or equal to log a to the power of b times b to the power of c times c to the power of a. And this is true because log is like an increasing function. So if one is bigger than the other, like this, then like the output of the log function will also be greater than the other output. Okay, so now we have to do something with this. Now, what do we know about our log laws? We can kind of split these up into different components, right? So the left-hand side is the same thing as doing log of a to the power of a plus log of b to the power of b plus log of c to the power of c. And then the right-hand side is the same as log a to the power of b plus log b to the power of c plus log c to the power of a. Now this is actually looking a little bit like what we had before. Does anyone have any clue as to what we can do next? Well, we can use another one of our log laws. So maybe we have seen this before, but say we have log base b of a to the power of m, then that's the same as move if you were to move the m down to the side, right? And then you took m times log base b of a, right? So what we can do is bring down all of these powers to the side. So then that would give us log of a plus b log of b plus c log of c. And we can do that for the other side as well. So then that's b log of a plus c log of b plus a log of c. Okay, this looks like something we can work with. So what would our two sequences be? What are the sequences that we are multiplying together? Hmm. Well, we could have, in our first case, when we have A, B, C, we can order them like this in terms of greatest to largest. I mean, sorry, what? Greatest to smallest. So we assume that A is the biggest, B is in the middle, and then C is the smallest one. And then corresponding to that, then we have log A, log B, and log C in that order. Right? So based on the rearrangement inequality, then where do we get our maximal? Well, we get our maximal permutation when you just multiply these in the same order, right? So then that would just give you A log A plus B log B plus C log C. And then that will be our maximal one, right? Now, on the other hand, to get the right-hand side, what are you actually doing? Well, you have A, B, C, and then you would be multiplying in, what would you be doing? A would be multiplied by log C, B is multiplied by log A, and C is multiplied by log B. So you can see that the largest one in the first sequence is getting multiplied by the smallest one in the second sequence. Now, the middle one in the first sequence is getting multiplied by the largest one in the second sequence, and then the smallest one in the first sequence is getting multiplied by the middle one in the second sequence. So, because of this, we know that it's not going to be maximal, right? And therefore, it's going to be smaller than this. Yeah, so this would be it proved for our first case. Now for our second case, once again, it's quite similar, but we just have to check which order we're doing things in. Okay, so we have A, C, B this time. So, the order would be this way around. And then when you multiply like these pairs, then it will be maximal, right? And then you will get what's on the left-hand side. But if you're looking at the right-hand side, we have A, C, B, and then what is it going to be multiplied by? Well, A goes with log C, C goes with log A, B goes, wait, no, sorry. C goes with log B, and then B goes with log A. All right, so now the largest one in the first sequence is being multiplied by the middle one of the second sequence. The middle one of this first sequence is being multiplied by the smallest one of the second sequence. And then now the smallest one of the first sequence is being multiplied by the largest one of the second sequence. So clearly these are not ordered the same, right? So the sum will not be maximal. And then it has to be less than what's on the left-hand side. So here. So there we go. We have successfully proved that a to the power of a times b to the power of b times c to the power of c is greater than or equal to a to the power of b times b to the power of c times c to the power of a. So yeah, and we also used a couple of our log laws to get into the form that we want. So I think conclusively, the rearrangement inequality is really quite useful. And a lot of the time it combines pretty well with other inequalities as well. Yeah. And it's just like often it is kind of intuition, but it's a good way of formalizing that intuition so that you can actually use it in problems, right? Okay, now the last question here, it's a combination of like power means and rearrangement inequalities, so I don't think we will be able to solve it in the remaining time. So let me just see if there's like any other problem that we could do. These ones are all quite hard. So let's just do a really quick recap of AMGM and then I'll come up with like a little problem. So for the AMGM inequality, that's telling us that the arithmetic mean, so the sum of all the numbers divided by the number of numbers, and it's going to be greater than or equal to the nth root of those n numbers. Okay, so let's just try a really quick problem as a refresher. So let's say that a plus b plus c plus d equals to 20. And then let's say find the max value of a squared b c d. Okay, I'll just give you guys like 3 minutes to give that a go. If you have any questions or answers, feel free to just unmute. Okay, has anyone got any solutions for this question? If not, I will go for it. Okay, alright. So we want the maximum value of a squared b c d, which means that we kind of want a to appear double the amount of times as b, c, and d, right? So what if we set up our AMGM like this? A over 2 plus a over 2 plus b plus c plus d, and then we divide it by 5 because that's the number of terms. And then that should be greater than or equal to the fifth root of a squared b c d divided by 4. Now we should be able to solve, right? Because this thing on the numerator that sums to 20. So we have 20 divided by 5 on the left-hand side, which gives us 4. And we know that 4 is going to be greater than or equal to the fifth root of a squared b c d divided by 4. Solving for that, so what's 4 to the power of 5? Can anyone tell me? No? Okay. I think 1024. I think 64. Yep, seems right. Okay, and then we know that 1024 is going to be greater than or equal to a squared bcd divided by 4. So then multiplying both sides by 4, then we know that the maximum value of a squared bcd is going to be 4096. Okay, so there we go, done. And then when are we able to achieve this maximum? When does equality hold? Well, that is when a over 2 equals to b, which equals to c, which equals to d, right? Because we require all of the terms to be equivalent for equality to hold. So if we know that all of these terms are equal and that they sum to 20, then we should be able to figure out what they're supposed to equal to. So, and we have, let's just try to write everything in terms of a then. So then we have a plus a over 2 times 3, right? Because all of these are equal to a over 2, and there are 3 of them. So then we get 3a over 2 plus a, that's going to be 5a over 2 equals to 20. So then a is going to equal to 8. Yep, and then because b, c, and d all equal to half of a, then that means that b equals to c equals to d is going to equal to 4. And we can see that this works. It's going to add up to 20 because you have 8 plus 4 plus 4 plus 4. And then if we try to figure out their sum, then we get 64 times 4 to the power of 3. And there we go. We have found the maximum value. Okay, any questions about this problem? Okay, if not, then we'll just finish up here. So we did some rearrangement inequality, did a bit of an AMGM refresher. Hopefully that one made sense. Let me know if you have any questions before we finish up. But otherwise, good job. And yeah, that's it. Okay, bye.